Hello guys, so today I'm here with a very interesting problem. This problem is find the city with the smallest number of neighbors at a threshold distance. So there are n cities and these cities are numbered 0 to n minus 1. Okay, and there are array edges, okay, where any of the component of this edges array, two-dimensional edges array is, a pair kind of, it has only two components from city and no, it has got three components. So first component is, the origin from where that, that edge starts and where it goes. So this edge is bidirectional. So there is no direction associated with that. You know, if an edge is from 0 to 1, we can consider that edge from 1 to 0 as well. And the third component is the weight. Okay, so from is the origin city and to is the destination city, but there is no direction associated with that. The origin can be destination as well, and the destination can be origin as well. I mean to say, there is no direction associated with any of the edges. The edges are bidirectional. Okay, and the third component is the weight. Okay, and then we are also given the distance threshold, that is an int value. And now it is asking, like, return the city with the smallest number of cities that are reachable through some path, okay, and whose distance is at most distance threshold. So we want to find out that, okay, at what distance, at, you know, let's say, from zero, we can, if you see this particular, this particular drawing, okay, if you see this drawing, then you can see that, you can reach from 0 to 1. You can reach to 2 via 1, you can reach to 3 as well via 1, or you can go to 3 from 0 via 0 1 2 3. So there are various paths, and we have to find out like which of these paths we can reach, and that path length is less than the distance threshold. So there are several things in this problem. First of all, we need to find the shortest path. Okay, so to find the shortest path, there are several ways. First of all, we can find where if there is a path in between two cities or not. First thing, and then we have also to the third thing that is that we have to check like via any other city if there is a shorter path or not. So this is the most critical check in this problem. So to solve this problem, okay, uh, we will do some things over here, and I'll explain what I'm going to do uh, as and when I'm trying to solve this problem. So first of all, I'll declare one int variable. Okay, so private int inf is equal to 1. So see, the value of weight at any point is in between 1 to 10 to the power 4. So anything which is more than that 10, you know 10,001 is infinity for us because it is more than 10 to the power 4. Okay, so we are taking this as infinity, and then what we are doing, that we are creating one graph of the cities graph, and then this graph will be, since there are n places and locations, okay, in the city, okay, there are n cities, okay, there are n cities, so actually there n is the cities. So n cities, so n into n, it's a matrix representation of the graph. So n into n we are doing, okay. And then what we are doing that, since it is n cross n, so there are n rows, okay. So there are n rows. So we are traversing through all these rows, and for each row, what we are doing that, we are filling that value of that graph of I, okay, graph of I with the infinity, okay. And also the other thing that I would like to mention here, that there is no self edge. So for the graph I of I is equal to 0. Okay. And then after this, what we will do, that we will, try to, since the edges are given to us, so we will populate this with the edges value. Okay. And whatever is remaining, that will be these default values. Okay. Edges. Okay. And then there is a source. So source for any edge is the 0th component. Okay. Edge destination is the edge first component, and weight is the second component, like this. Okay. And then what we will do, that we will, uh, after doing this, what we will do, that, graph of source destination is equal to weight graph of destination source. This is also equal to weight, because, since this is a bidirectional, so from source to destination, whatever is the weight, the same weight will be from destination to source as well. So this is the way we are populating the graph matrix with the correct weight value for each and every edge. Okay. After we have done this, what we want to do, that, we want to check what is the shortest path. And to check the shortest path, we will check through via matrix. So via matrix will start from 0, because the first city is, cities are numbered from 0 to n-1. And via will be going till less than n, because n-1, and then plus plus via. Okay. And then for int I is equal to 0, I less than n, because they are n cities. So we are taking, like, for each I to j path, we are doing this for int j is equal to 0, j is less than n, plus plus j. Okay. And then what we will do, that, graph of I j is equal to math.min. Okay. Graph of I j. So this is one component, and the other component will be graph of I. So it will go to some other vertex. So vertex, first we will choose the vertex 0. Okay. And graph of, and from that vertex to the destination vertex, the jth vertex. And we'll take the min out of all this, and then we'll put in that. Now, after we have this graph populated, I mean to say the direct path. So first of all, we are considering the direct path, and then we are checking if via any other vertex, if that, you know, uh, path is there, by any other vertex. So this we have populated. And after this, what we will do, that we will, take this count. Okay. So count is equal to 0, because we want to, for each of the, cities, what is the other cities which are within that threshold distance. So this is will be in the count variable. Okay. And then we will take this value. So value is, any city can reach to the any other city. So the total cities are n. Okay. And then the third thing is that city that, we want to return. Okay. And that is, we are initializing it with -1. Okay. And then what we will do, that, we will go through each and every row of the given graph, and it will be, like this. And then what we will do, that, then what we will do, that, we will take, and for each of the int j, colon graph of I. So ith row of the graph is graph of I. Okay. And then we will check if j is not equal to 0, because self edge is always 0 and we don't want 0 to be considered here. Okay, all other edge weights are more than 0. Why? Because in the constraint it is clearly mentioned that it is greater than 1 and less than equal to 10 to the power 4. So it is not going to be 0. So we can safely preclude that 0, because if you consider 0, then it is obviously going to be less than threshold value, and that will that will give a result which is +1, which is not correct, which will be the correct value +1, which you don't want. So we will check if count if j is less than equal to distance threshold okay, distance threshold. If it is like this, then what we will do, that we will be incrementing the count. Okay, and after we have incremented this count, we will check if count is less than equal to val. If it is less than equal to val is the, for the particular, the current maximum value. So if it is less than equal to current, then we are taking this current is equal to the values to be current, and then ct is equal to the index. Index is the row. So this ith row is going to be the this. And after this, we will, what we'll do, that, we will return this city. Okay. So I hope this solution is clear to one and all of you. Okay. With this, I would just like to run this solution and let's see what's happened. So we are getting a wrong answer. Oh, ho, ho. Yeah, mistake is pretty much, we have to make it 0 again, because for every row we have to start the count from 0. Okay. So now it's perfect. Now I'll submit it once more. Let's see how it performs. Perfect, perfect. So this is, beating other solutions. It's a decent solution. If there is any doubt, please, let me know in the, comments. I would also like to mention that this particular thing is, it's an implementation of Floyd-Warshall's, all pair shortest path. All pair shortest path between any two indices of the any two vertices of the graph. Okay. So this is the implementation of Floyd-Warshall all pair shortest path between any two vertices of the graph, and this we have used in this problem to solve this problem. uh, if there is any doubt, please post it in the comments. Please post appreciative comments as well. I would very much feel encouraged. Thanks a lot. With this, I would like to, bring an end to this video. Best wishes. Thanks a lot.